Page 7 of the scheduling notes. We're on to a new section, which is concurrent execution. So parallel execution, I think, is fairly self-evident. You have multiple processes or threads, and they're running on different processors at the same time. And in parallel execution, usually the programs communicate with a message passing library. Concurrent execution is a little different than that. What you have is multiple threads of execution that may be running on multiple processors, or they may be running on one processor, and you don't have any promise on what order they run relative to each other. So for each thread of execution, the instructions will run in the right sequence within that thread, but they could be interleaved with execution of instructions from other threads. I'm going to revert back to my task terminology. Task. So a task has a thread of execution. A thread of execution just means the order that the instructions execute in. So task executions are interleaved on one or more processors with indeterminate order. So if you run the same multi-threaded program more than once, the one thread may run before the other. It can change depending on what other things are happening on the processor, other programs are running, inputs and stuff like that. You could have one task run from start to finish and then the next one run from start to finish, or in the extreme, if they're sharing the same processor, you could have one instruction run and then the other. There's actually a technique, hardware technique for that, called simultaneous multi-threading. Actually, that sounds more like fully parallel. But anyway, just kind of an aside. I said that the instructions within the thread of execution run in the correct order. That's actually not entirely true on modern deeply pipelined processors like the Intel Kaby Lake processor line, or AMD's Ryzen 7 and Ryzen 5 processor lines. They will actually execute instructions out of order, but somehow preserving the inter-instruction dependencies, data dependencies and control dependencies. It's pretty neat, but definitely outside of the scope of this course. You learn about that kind of thing in ECE 320. We're going to look at an example of concurrent execution. We have one processor for this example, and that's going to be the case for this course. We have 3 tasks of equal priority, and we're going to use round robin scheduling. The name round robin comes actually from, I think, around the 1700s, from seafaring days. So on these old sailing ships, the captain had ultimate authority. They could condemn and have people executed, flogged, and so on. And so if the senior, I forget what they call them, the people that are behind the mast, so the first mate, second mate, and the navigators and all those people, if they were making a request to the captain, if they were petitioning him, they would put their names on the document in a circle so that the captain could not tell who signed first and who was kind of the ringleader. So it had the name Robin Round, or Ronde. It's French, which I can't pronounce, but basically it means like a ribbon of signatures around the petition. So that's where that name comes from. There's a good movie based on those times called Master and Commander. It's based on a book by Patrick O'Brien. Sounds a little Irish, but anyway, starred Russell Crowe. So if you're looking for something to do, there's a good movie. So what we're going to do is we're going to look at the timing diagram, and I need to make a timeline, and I'm going to leave a little space on the left. So there's my timeline, and I want to have 7 segments here. 1, 2, 3, 4, 5, 6, 7. And we're going to have 3 tasks, which I will denote. I'm going to leave a blank line there. T1, T2, and T3. And so task 1 will start in this first segment, and it will be running while its line is high, and then when its line goes low, it's not running until it's its turn again. So task 2 will start running where task 1 leaves off, and then when it finishes, task 3 will run. So for the first time slice, task 1 uses the processor. For the second time slice, task 3 uses the processor, and then that order repeats indefinitely. Okay, so let's add a couple labels here. This unit here is called a time slice, and it's typically 5 milliseconds. That's on RTOS2. Also, I think Linux, it depends on the processor, but 5 milliseconds is not uncommon. Time slices used to be longer, something like 20 milliseconds, but processors are faster now. It can switch between these tasks fairly quickly, and so making the time slices smaller makes it appear more like simultaneous execution. Now T1 is in the running state while the bar is high, and it's in the ready state while the bar is low. So it got suspended at this point here, and then it will be resumed at this point here. So this is an example of a context switch. So the execution context of task 1 is stored or saved, and the execution context of task 2 is restored at this point, and so then it starts executing. So basically at every time slice we have a context switch happening.